Hello and welcome to this short clip on nucleophilic substitution mechanisms. It's a little bit beyond A level, but it delves into something called Sn1 and Sn2 nucleophilic substitution mechanisms. As you could probably guess, what it actually means is there's two possible ways in which a nucleophilic substitution can proceed, and it depends on the stability of the carbocation produced during the mechanism. And although it's not governed directly by Markovnikov's rule, the stability of carbocations that you'll come across at A level while studying Markovnikov's rule are closely linked to what's happening here. Now, a key fact in most, if not all, reactions is they go through several steps, certainly in organic chemistry, before the final product. And this might include ones that you've studied as single-step reactions. So the rate of reaction overall is governed by the slowest step. And as such, this might be dependent on the concentration of one or more species. And this would be called the rate-determining step. Now, the idea of a rate-determining step is in A-level chemistry, but you'll have studied it not while you're doing nucleophilic substitution, you'll have come across it whilst you're doing reactions and rate orders in the second year. So here's an application, basically, of that idea to something you might have studied in your first year. So the key difference between Sn1 and Sn2 is the number of species whose concentrations are in the rate-determining step. Now, I'll say it a bit better than that. The number of species that determine the rate-determining step. So an Sn1 mechanism only depends on the concentration of one species in its rate-determining step, whilst an Sn2 mechanism will depend on the concentration of two species in its rate-determining step. And there's a little key at the bottom of the page that explains what the parts of Sn1 and Sn2 terms actually mean. The S stands for substitution, the subscript N, capital N, stands for nucleophilic, and the number 1 or 2 equals the number of species whose concentrations influence the rate of the reaction via the rate-determining step. So let's have a look at this in terms of a common and familiar nucleophilic substitution, probably the first one you came across, nucleophilic substitution of OH onto a haloalkane. So the type of mechanism, e.g. Sn1 or Sn2, by which this particular reaction proceeds, depends entirely on the structure of the initial haloalkane. So looking at primary, secondary and tertiary haloalkane structures, imagine that the halogen X was removed and you just had a carbocation. Just like in Markovnikov's rule, the more carbon-based chains or groups that are attached directly to the positively charged carbon, in other words, what's been highlighted in pink, the greater the stability of the carbocation and the more likely it is to form and exist for long enough to undergo a different type of mechanism route. This is due to something called inductive effect. When you have alkyl groups that are directly attached to a carbon that's positively charged, they will tend to push electrons towards that carbon and stabilize it. So this might help explain to you why the tertiary structure of a carbocation is more stable than, let's say, the primary or the secondary, because there are more instances, more examples on the third tertiary carbocation of inductive effect taking place. So you have 3 R groups all undertaking the inductive effect. They're electron donating, in other words. So that, in other words, shores up or stabilizes the positively charged carbon, which I've now highlighted in pink. Therefore, this can exist as a species on its own for enough time to actually undergo a slightly different route of nucleophilic substitution, which we'll look at next. So let's look at the Sn2 mechanism to start off with. This is the one that you're used to. So imagine you had OH-, for example, as your nucleophile. So adding on the correct dipoles, you'd obviously have the lone pair moving towards the delta plus carbon. And the carbon-bromine bond would break by heterolytic fission. Now this happens simultaneously, so straight away you can see that the concentration of OH- and the concentration of the original haloalkane are going to affect the rate-determining step. So remembering that bond breaking is endothermic, there's going to be an energy requirement to break the carbon-bromine bond by heterolytic fission. So that first step is slow. That means that's going to be the rate determining step. And as such, it's the concentration of both the hydroxide and the original haloalkane that determine the rate of that particular step. So because two species equally influence the rate of this rate determining step, it's called an Sn2 mechanism, and that's covered in the rate equation in the bottom left of the screen. So let's have a look at a couple of animations that might help explain it a little bit further. So if we look at the left-hand animation first, you can see it's essentially the same as what we've done up in the top left-hand corner. So what has to happen is that the CBr bond has to break. That's the rate determining part of it. And if you look at the animation on the right, the activation energy for that has to be overcome. But as that's overcome, and then the Br leaves, the energy of the chemical reaction, the energy within the chemical system, drops. So therefore, as it drops, it stabilizes, and that part is much faster. So the slow step is up to about here, and after that, things start to speed up. Okay, so now let's have a look at the equivalent for Sn1. So this time we've got a tertiary haloalkane. You can see that from the three CH3 groups. But the actual mechanism starts slightly differently. Once you produce a tertiary carbocation, it's a little bit more stable than the secondary or primary carbocations. It's more likely to be produced. Therefore this mechanism, the Sn1 version, is the one that the tertiary carbocations, the tertiary haloalkanes can follow. In the second step, the hydroxide ion can very quickly attack the carbocation and form the final product of 2-methyl-propan-2-ol and the Br- ion. So I've completed the mechanism at the top, so you can see the slow rate step and the fast rate step. So if we look at the rate equation, only CH3,3Cbr is involved in this first step, because that's the slow step, that's going to be the rate determining step. So it's an Sn1 process, because there is one molecule involved. The OH- isn't involved until the second step. The second step is the fast step, which doesn't affect the overall rate of the reaction. It doesn't control it. So therefore, OH-, its concentration, that is, will not be in the rate equation. So for these reasons, this is an Sn1 nucleophilic substitution instead of an Sn2 nucleophilic substitution. Now one thing we haven't looked at is secondary haloalkanes. We looked at primary ones and we looked at tertiary ones. So what do secondary haloalkanes do? This is a little bit more complex. They can actually undergo Sn1 or Sn2. So if we look at a secondary haloalkane, we'll see that they're actually chiral, or the example we're going to look at is a chiral molecule. So it brings in a little bit of optical isomerism as well. So if we look at the two enantiomers of 2-bromobutane, so if you were to hydrolyze this using OH- ions, two possible products would be formed. So for two different reasons, Sn1 or Sn2 are a possibility. For Sn1 to occur, you have to have a stable carbocation. There's just enough stability in a secondary structure for this to be happening. For Sn2 to happen, the approach of the OH- from behind has to be unhindered, therefore bulky alkyl groups will get in the way. So if you've got two possibilities, what might affect each one? This requires us to delve a little bit further into what actually happens during the process. So if we take an Sn2 mechanism, the incoming nucleophile has to be able to reach the carbon in the CBr bond. A transition state forms when the 3D orientation of the four groups attached to the carbon undergoes inversion. So looking at the right-hand animation, the transition state is about to happen. There you go. So do you notice that what's happening to the hydrogens is they're starting to point in the opposite direction, to the right? This is called inversion, and this takes place in Sn2 nucleophilic substitution. In other words, the OH minus nucleophile approaches from the left-hand side as opposed to directly approaching the bromine, because that way it avoids repulsion by the delta minus charge on the bromine, the partial charge. So the nucleophile approaches from the opposite side of the carbon-bromine bond to the delta negative bromine atom. What this causes is inversion, like we've just said. Let's now look at the Sn1 equivalent. So this is the Sn2, where there are two species involved in the rate determining step, the OH minus and the haloalkane. The Sn1 version is when there's only one species involved, and that's the actual haloalkane itself. So this animation probably goes a little bit quickly for me to follow, but I'll start it off and I'll see if I can keep up. So we start off with our bromo 2-bromobutane CBr bond breaks, that's your slow step, producing a planar carbocation. In the second step, the planar carbocation can be attacked on one side, or it can be attacked on the other side. Each one produces a slightly different orientation of the four groups around the chiral carbon. And those two versions are a racemic mixture, a 50-50 mix of the two enantiomers. So this is an Sn1 mechanism because the slow rate determining step will determine the whole speed of the reaction. Step 2 and step 3 are fast. So therefore, in the slow rate determining step, there's only one species involved. And that species is this here. So it's your 2-bromobutane. So the difference between this one and the Sn2 mechanism is that during the inversion process you can actually get two possible enantiomers. You wouldn't be able to get that with a primary carbocation because it wouldn't be a chiral carbon. So how come there are two possible ways in which you could, in which the groups could orientate themselves? The key lies in the trigonal planar carbocation. It's a flat molecule, so therefore the OH can attack from above or below, or in this case the CH3 OH can attack from above or below. If it attacks from above, that creates one orientation, or if it attacks from below, it can create another, which are the two orientations you see now at this point, your racemic mixture. So let's have a look and see if we can apply this to a fairly advanced question. It's not an exam question by any stretch, it's not an A-level standard question, it's beyond A-level, but it's worth having a think about it and seeing if we can deduce our way through it. So this question asks us about 2-bromobutane. We looked at 2-bromobutane in the last couple of slides. So what you're looking at is the haloalkane hydrolyzed with aqueous sodium hydroxide. And what's interesting is it says that some molecules react by an Sn1 mechanism. Sorry, I'll improve that colour for you a little bit. There we go, that's better. Some molecules react by an Sn1 mechanism and others by an Sn2 mechanism. So let's pause it for a second and just collect the information that we know from those those few words. So 2-bromobutane has a secondary structure and it is also chiral. So it's worth bearing those facts in mind before we go any further. So the mechanism they want is Sn1 hydrolysis. So only the bromobutane's concentration affects the rate of that reaction, because the rate determining step is going to involve the breakage of the carbon-bromine bond. So let's start the mechanism. We haven't actually scored any marks yet, all we're doing is collecting ideas. So the mechanism starts by the breakage of the carbon-bromine bond, like we just said. So putting in my dipoles and my curly arrow, that shows the CBr bond breaking. You'll notice what I haven't done is drawn the three-dimensional structure like it's over on the right-hand side of the page. I've just kept that over there as a reminder to myself that I'm dealing with a three-dimensional structure that happens to also be containing a chiral centre. So that's the rate determining step. So that produces a trigonal planar carbocation. RDS stands for rate determining step. So I also need to release my Br minus, that also needs to be there, like so. Now the next thing to happen is that my trigonal planar carbocation is attacked in a fast step by OH minus. And that gives me my final product. So I'm going to draw a line, a dotted grey line between the slow rate determining step and the fast step, but they happen in succession to each other. So the next part of the question asks us to outline the mechanism by Sn2 hydrolysis, again identifying the rate determining step. So I start by drawing my species and putting in the dipoles. So remembering that my OH minus attacks from behind due to repulsion from the delta minus Br atom, the next thing that happens is obviously the CBr bond breaks. So the next thing I do is I show my transition state, just that split second where there is a bond forming between the oxygen and the carbon, and a bond breaking between the carbon and the bromine. And the breaking of the carbon-bromine bond is much quicker now, because the energy is being provided, the activated energy has been overcome for the initial heterolytic fission. So the next part of the question, it talks about bromobutane's chirality. Let's move it down and just highlight that particular part of the question. Now what you don't have to concern yourself with is what is the orientation of the groups in D-bromobutane or L-bromobutane. The D and L isomers stand for dextrorotatory, which is rotating the plane polarized light to the right, or levorotatory, which is rotating the plane polarized light to the left. How you actually draw them out on paper is not necessarily for this particular question, even though it looks like it might be. So let's read the next part of the question very, very carefully. It says, if D2-bromobutane were to be hydrolyzed, in other words, if one of the enantiomers were to be hydrolyzed, it says, state and explain whether you'd expect the product to be D-butan-2-ol, L-butan-2-ol, or DL-butan-2-ol. Now, DL-butan-2-ol is a racemic mixture, like we talked about before. So what the question is really asking is, will there be inversion during the process, and will one or both of the isomers form? So the Sn1 mechanism, let's have a look at what would happen here. So if you remember the animation where we had the Sn1 mechanism, we formed a trigonal planar carbocation. So because you get a trigonal planar carbocation in the Sn1 mechanism, there's an equal probability of OH minus attacking from above or below. That's all you really had to think about, not what the structure of D or L might actually look like if you had to draw them on paper. So it's a slightly sneaky question in the way it's worded. is making it sound like it's asking for more than it actually is. So now let's look at Sn2. Now to help with this one, I've brought back the animation that we had earlier. So if we take a moment to have a little look at it, what's happening is that both of those species are required at this point to form the transition state to then go on to create the substituted product. So inversion takes place during that process, doesn't it? There's only one particular product made, not two enantiomers. So I know technically that the example that I've got at the bottom is not 2-bromobutane, but if you imagine that one of the H's is a CH3 and another one of the H's is a C2H5, I'm sure you can try and follow it in your mind. So this must mean that the identity of product is the inverted version. So if you invert D2-bromobutane, when you substitute OH minus onto it, you will get L-butan-2-ol. So as Br leaves from one side, the OH minus approaches from the other. Therefore inversion of the groups occurs, so the other orientation of the product in stereoisomeric terms. So it's L-butan-2-ol being made from D2-bromobutane. Okay, so hopefully this was a reasonably useful extension of your understanding of nucleophilic substitution. Please don't worry that anything like this would come up in an A-level exam, because it wouldn't. It is definitely extension material. It's definitely much more university level. But like all the extension clips that I've put on my channel, they're designed just to take you a little bit over the horizon from where you are right now at A-level, just to give you a look and see how far we can push things. So once again, thanks for listening, and hopefully see you soon. Bye.